That's another Dibs Physics video.
What's up, physics fellas? How are we doing on this fine day? What I do want to do in today's video, it's going to be a little bit shorter, is first and foremost, I want to go over our last two homework assignments, which were all about motion graphs. Hopefully give you guys, a better feeling about motion graphs and how to answer those questions. After the conclusion of that video, I would like you guys to then do yet another motion graph assignment, which would be taking of a picture of and uploading to Classroom for another homework / classwork grade in this case. And then you also have a CASEL Learning due by Thursday at 3:15 p.m. That will be an assessment grade. So I'm going to give you guys retries as half credit, and it's going to be a 10-point assessment. So if you get a 10 or 100, you'll get a 10 out of 10, obviously. If you get like a 92, you'll get a 9.2 out of 10. So that's how that's going to work out. And hopefully that should boost your guys' grade. You could do this at home. You could do it with whatever materials you've put together from class time. Now, what I want to do today is just go over some of these and just make sure that you guys have the the tools that you need to be able to answer these questions. So let's jump in here and take a look at velocity graphs 1. So we have this first graph here that we were taking a look at. And in this graph, I don't know why that's there, we go. In this graph, we have the motion of a train. Now, a couple things to note here is that this is north and this is south, right? We know this because here in the description it says the train originally faces north. So that's telling us that north and south, and it's giving us our positive and negative directions. North being positive, south being negative. All right, so now let's go through and let's answer those questions. All right, what is the magnitude and direction of the train's acceleration in the first 10 seconds? So the first 10 seconds is there from A to B. Each box is about 10 seconds. So we have to come back to how to find acceleration. So let's jot some notes down, maybe off to the side here. Let's just jot some notes. So firstly, if we have a position versus time graph, right? Let's say we want to get displacement. We read the axis. If we want to get velocity, we look at the slope. And if we want to get acceleration, we can't really get that, but we can tell whether or not it's a curvy graph. Now, if we have a velocity versus time graph to get these things, to get displacement, that's where we have to do our little area between the line and the x-axis trick that we do. And if we want to find velocity, here we just read our axis, and if we want acceleration, we find the slope. So this little chart is a nice little cheat sheet, if you will, for finding all of the different things to describe the motion of an object from a motion graph. So let's jump back to our graph here, and we're talking about the first 10 seconds. We want to find acceleration. So if we go back to our chart, I'm not going to go back to it right now, but hopefully you guys can. We know we need to find the slope. So acceleration is going to be a change in velocity over a change in time, aka slope. If we actually look at this, delta y over delta x, these are really the same equation, aren't they? Right? The y-axis in this case is velocity and the x-axis is time, so we can look at it like this. So let's go find the slope of this graph. I'm going to zoom in really big here, so hopefully we can all follow along. So I'm going to do rise over run. So here's my rise. What did I do? I went up by a positive 6 meters per second. Right? And then my run from A to B is going to be 10 seconds. So let's go back and plug these values in and solve the problem. All right. So our rise, or our change in velocity, was a positive 6 meters per second. And run 10 seconds. So we get 0.6 meters per second, or meters per second squared. Now, what's important to remember here is this question asks us for the magnitude. That's what we just found. So this is the magnitude, 0.6 meters per second squared, and direction. So the direction is whether or not this is positive or negative. We got a positive answer here, being careful, which means we're going north, as we already defined that. So the final answer is 0.6 meters per second squared to the north. All right, now let's get into these next couple questions. And with these, I'm not gonna really write the answers down. I'm just gonna kind of be like highlighting them on the graph as we go. So let's look at intervals where the train is speeding up. This is probably one of the ones you got wrong. So if you're feeling confident about this, well, we're gonna find out. So let me get rid of our slope stuff there and come back to this. Where was the train speeding up? Well, from A to B would be a good answer, right? A to B, the train was indeed speeding up. I can see that because my velocity goes from 0 to 6 meters per second. I increased my speed. However, what other intervals were we speeding up? We've got A to B here, but what else? So A to B, and guess what the other answer is? From D to E. That's weird. I'm gonna guess a lot of you put E to F, but that would be wrong, right? Just because it's a positive slope does not mean we're speeding up. And this was part of the last homework we did, where we talked about acceleration direction, right? Like, what's the direction of the acceleration in a certain situation? So here, there's a change in direction that occurs. After point D, all of the velocities become negative. And that's kind of an interesting thing. When those velocities become negative, now the opposite rules apply. So a negative slope would be a southward acceleration when we're moving south, which means we're speeding up. And we can tell this again just by looking at those numbers on the axis. At point D, we are at 0 meters per second. And then at point E, we're at negative 6 meters per second. So we increased our speed from 0 to negative 6 meters per second. Kind of interesting. So let's kind of highlight this. A to B, we're speeding up, and D to E, we're speeding up. So I'll just kind of make a note. Yellow is increasing speed, right? And now let's take orange highlighter. Oops. Let's get rid of that. Let's get a different color highlighter. Let's go with orange. Cool. So now orange highlighter we're going to use for now decreasing speed. So decreasing speed is going to be our orange highlighter. So now, where is this thing slowing down? That was our next question. So again, look at that y-axis and look at the values that we have. From C to D, we're slowing down. Our velocity goes from positive 6 meters per second to 0. And then same with E to F, we're slowing down. So from E to F, we are going from negative 6 to 0. So we're going 6 meters per second south to 0. So we'd be slowing down there. And then let's grab a different color highlighter yet again. Let's get some green going, right? From F to G and B to C, what's happening? I think a lot of you might say, oh, it's not moving, but that would be incorrect. In this case, the green represents constant speed, right? Here we're at a constant speed of 6 meters per second from B to C, and from F to G we're at a constant speed of 0 meters per second. So from F to G we are certainly not moving, right? But from B to C we are moving at a constant speed of 6 meters per second. So let's see what questions we answered here. We answered, when is the train speeding up and when is the train slowing down? But when is the train traveling north is now an interesting question, right? It'll be traveling north whenever our train has a positive velocity. So our train has a positive velocity from A the entire time until D. So from A to D, we have a positive velocity, so we're traveling north. Then when is the train traveling south? Well, we'll be traveling south whenever we have a negative velocity. So from D to F, we're traveling to the south, right? And this is a little weird. You know, I'm willing to bet a lot of you said A to B, we're going forward, and then C to E, we're going backwards, right? You're confusing the two types of graphs that we have. We have a velocity time graph here, and we've got to remember the fundamentals that we talked about in some of our previous videos, right? When describing the motion of an object, really the key thing that we need to think about when describing the motion of an object is velocity, right? That's what's going to tell us the motion of an object. So if we have a velocity versus time graph like we do, to really describe the motion of an object, we've got to read the axis, right? The slope is going to tell us all about our acceleration, which is something else. Okay, so now let's look at the next question. When does the train change directions? So the train certainly changes directions here at point D. So the train changing directions directly at that moment in time, point D. And then how far does the train travel from A to B? So this is where it gets weird. This is where this worksheet becomes very interesting. So how far on a velocity versus time graph? We're talking now about the area between our line and the x-axis. So let's get into this here. I'm going to actually just kind of erase everything on here just to clean this up a bit. Okay, get rid of this too. There we go. All right, so from A to B, what I'm going to do, I'm going to highlight the line here as purple from A to B. So that's my line from A to B. Then what I'm going to do is I'm going to highlight the x-axis from A to B. And then what I'm going to do is I'm going to fill in the in-between here in this color. Right? So right now I've got this purple triangle. What I want to do is I want to find the area of that purple triangle. So let's zoom on in here to find the area of this triangle. Let me get this guy going. Let's go really skinny. So yeah. All right. So the height of this triangle would be 6 meters per second. The width of this triangle is going to be 10 seconds. So if we want to find the area of this triangle, we have to find the area equation for a triangle. So let's go do that work off to the side here, right? The area of a triangle is 1/2 base times height. So in this case, we're looking at 1/2 our base, which is 10 seconds, times our height, which is 6 meters per second. So that's going to be half of 60, which is 30. And what's cool is the units actually cancel out here. Seconds cancels with seconds, so we end up with 30 meters as our answer. So we've got 30 meters that we've traveled. So if we were showing our work, there's the equation, substitution with units, and our answer with units. So what I'm going to do is I'm just going to write on top of this 30 meters. All right, so we figured it out by finding the area between the line and the x-axis. So all that work here goes into this guy, which is done. We finished this one, we answered this, awesome. But now, this next question, the next two are really spicy. What is the total distance the train travels in this graph? Oh my gosh. So now we've got to find the area between the entire line and the x-axis. So this becomes a little tricky because, okay, the line is changing. So what we've got to do is break this up into shapes. So let's do B to C next. So from B to C, I'm going to draw my line, and I'm going to draw the x-axis here. So I've done that from B to C, right? And now I'm going to color in that region that we create. All right, so let's color it in, do the best I can here. Yeah, here, maybe I'll cheat a little bit. There we go. Yeah, that's better. Color it in. You guys can just like shade it or something, right? So now I've got to find the area of this guy. So what am I doing here? I'm going to do base times height. So in this case, my base is 10, 20, 30 seconds times my height, which is 6 meters per second. So let's break out the old TI calculator, you know what I'm saying? All right, let's turn it on. Here we go. See, there she is. All right, so we got our calculator. We're going to do 6 times 30. Those of you that are good at math are going to know that's 180. There we go. So now we've got 180 meters done from B to C. So now let's go through and do from C to D. I'm just going to alternate between red and purple. So here's purple again. Right? So there's my line and there's the x-axis, and I'm just going to fill in this shape. So we make this shape by finding the area between our line and the x-axis. A lot of times in physics we call this finding the area under the curve. So if I go to do this, I'm going to be doing 1/2 base times height. So I'm going to be typing into my calculator 0.5, so it's 1/2, times the base of this triangle, which is in this case is 20 seconds, and the height of this triangle, which is going to be 6 meters per second, so times 6. So I've got now 60 meters as the area there. And now what I can do is I can just keep this going, man. So I'm going to do this now from D to E. And this is where it gets a little tricky from D to E, right? So if I look at it here, if I draw my line from D to E, and then I draw the x-axis from D to E, we're not finding anything down here. We're finding this space, right? This triangle, again, between the line and the x-axis. So let's fill this guy in. Now, what you might notice is the size of this triangle is pretty much the same as our last triangle, right? So could we just write 60 in there? Now, oops, I don't want to do that because I want to, my computer's exploding. Hold on. Hey, all right. I don't want to do that because what I want to do here is look at these axes for a specific reason. So the time here is 20 seconds on this x-axis, right? 2 boxes is going to be 20 seconds. But the height of this triangle is a -6 meters per second. So if I go to do this math on our calculator, we're going to do pretty much the same thing. 0.5 times 20 times -6. And when I do that, I'm going to get a negative number. I'm going to get -60 meters. So I'll put that in here, -60 meters, right? And what does that negative sign mean? That means we were moving backwards, right? Which is hugely important for this question. So being diligent with your negatives and positives really pays off, I think, in this activity that we're doing here. Really in physics in general, honestly, if you pay attention to your negatives and positives, you're gonna have a good time in physics. So here I go. Let me get rid of the calculator here, get out of the way for a second. Right, as you can see, I drew a purple line along the x-axis and a purple line along my line, and I'm just gonna fill in that space here. Right, so I get another triangle here that I've got to fill in, and I've got to find the area of this triangle, and then we're pretty much done. We're going to talk about what happens in F to G in a second. All right, here we go. A little sloppy, but hey, we'll take it. So we'll do that same math again. I'll bring the calculator up, except this time we've got 0.5, 1/2 base, which is going to be 40 seconds this time, times our height of, again, -6. So we end up with -120 meters. Now, do we have to do anything for F to G? The answer is no, because if I draw a line along the line and a line again along the x-axis, what do we notice about that? I realize the calculator was in the way. There's no area between, which makes sense because no distance was traveled if my velocity was 0 meters per second. So this little trick that we've got really works in every scenario, and hopefully you guys didn't catch me missing my units there. Whew. Okay, so now we've found how far the train has gone in all its different phases of motion. So if we want to find the total distance this train has traveled, we're just going to add up all these values. So I'm going to do 30 plus 180 plus 60, and then we get to the negative values. I'm just going to do plus 60 because if I'm asked about distance, the direction we traveled doesn't matter. So I'm just going to add these values in, plus 120. So I just add them all up, I hit enter, and we are looking at a total distance of 450 meters. So we'll come in here, the total distance here is 450 meters. Nice, that one's done. But what was the total displacement? So this one is a little different. Displacement, we do care about that direction. So we're gonna make sure from D to F, the places where this object was moving backwards, that we do take that into account. So all we've got to do now is just keep our negatives, 30 plus 180 plus 60, right? So if I do that, I'll know this train went 270 meters north, because those are all of the distances we went north. And then we have 60 plus 120, 180 meters south. So if I could do it like this. I could say, hey, I went 270 meters total north minus 180 meters where I was going south, and now we're looking at 90 meters. And we got a positive answer, so we know it's north. And we could have did this an easier way, honestly. We could have just, went, okay, 30 plus 180 plus 60. And then, okay, now we got our negatives, right? So minus 60, minus 120. So we could just do it all in one step, which you guys know I'm a fan of, right? Don't be a numbers girl. Do everything all in one step. So now we're looking at 90 as our answer, same as we got before. So we have a displacement now of 90 meters. So let's head on down, let's answer it, and then let's go to the next graph. I'm not going to answer all of the questions in this next graph because I think it's pretty much the same. But one of the things we do want to note early on, right, is that with this graph, we start with the student running west. So that means in this case, we have west as our positive value, which means our negative values are east. So that means we can kind of grab a few things really quick. E is the point in which we change direction. So we kind of know that that's the case. We're going to change direction at point E. And we should be able to figure pretty much everything out here. So next, the first question here, where does the student experience the greatest acceleration? So let's just take a moment here to come back to kind of this little chart that we made. If I want to know my acceleration on a velocity versus time graph, I need to look at my slope. So I'm going to look at this and I'm going to see, okay, greatest acceleration. That means I need to find the area on the graph where we have the greatest slope. And to me, that is, not to me, it is right here from B to C. That is where the graph is the steepest. Regardless of whether it is positive or negative, that is the steepest part of the graph. So this student has the greatest acceleration from B to C. Okay. What intervals is the student speeding up? So again, we'll kind of come back with that same thing. The student is speeding up from E to F. Same reasons as we talked about before. We're going from 0 to negative 4 meters per second. So we're going from 0 to 4 meters per second to the east. B to C, D to E, all of those intervals, the object's actually slowing down, which kind of answers our question, when is the object slowing down? which is the next one. The object is slowing down from B to C and D to E. All of those points, the object is slowing down. When is the student traveling to the west? So to answer that one, we are going to the west from A to E, right? So we are traveling to the west this entire interval because all of these, we have positive velocities, and positive velocities mean we are traveling to the west. All right. Then we have, when does the student change direction? Well, that would be when the velocities go from positive to negative or negative to positive. So point E is the point at which this object changes direction. How far does the student travel from A to B? So again, we've got to do our area trick. So from A to B, we go here to here, to here. So I'm finding the area of this rectangle here. Okay, and this one's pretty easy, guys. It's a rectangle, so here, maybe I'll just write it in here. This time the height of the rectangle is +6 and the width is 3. 6 times 3 is 18, so we're traveling 18 meters right here. Awesome, so we've got 18 meters. Then what is the total distance the student travels? So now we got to play that whole game again. Where this one gets a little tricky is right here from B to C. The reason why, kind of take a look at this. If here's C and then here's my x-axis, that's kind of awkward, isn't it? So I've kind of got to break this into two shapes because this is a trapezoid. Anybody want to find the area of a trapezoid? Nah. So what we want to do now is just find the area of this rectangle and the area of this triangle, right? So this is 1 second by, I believe, 2 meters per second. So 1 times 2 is going to be 2 meters. And then this is actually going to be the same. It's going to be 1/2, 1 times 4, which is going to be another 2 meters. Then we'll do now from C to D, there's the line, there's the x-axis, there we go, nice little rectangle. So now we've got 2 times 2, which is going to give us 4 meters, right? And we're just going to keep rolling along with this here. So from D to E, if you guys do that one again, there's D to E, there's the x-axis, we got ourselves a triangle. Do the math, we're looking at 2 meters, okay, awesome. Then from E to F, right? Now this is where, again, we're gonna be very careful. Our velocity here is a -4, so this is -4 meters per second, and this is 2 seconds. So 1/2 base times height, so it's going to give us an answer of -4 meters. There. And now we'll do our last section, which is F to G. There's the x-axis from F to G. And this is the shape that I've got to fill. Yet another rectangle. So this rectangle is, again, -4 meters per second by 4 seconds. So that is going to give us 16 meters, and it's going to be negative again because we're going in that opposite direction. So what can we do is we can figure out how far we have gone kind of in each direction. So why don't we just add all these up? So we have 22, 34, so we've gone a total of 28 meters west in this initial section here, right? And then when we were traveling east, we have 20 meters east. So our total distance traveled is going to be that 48 meters, okay? So we're going 48 meters total as our distance, and our displacement is going to be 8 meters to the west. I think that hits all the questions. Let's double check. Yeah, there we go. Awesome. So hopefully this kind of helped you guys find things. Again, I just want to come back to this. This is really our bread and butter, understanding how to get info from these graphs. It's no shame to have this written down somewhere as like a little chart for getting info, okay? So that's pretty much it. And on to the next one. All right, This sheet was also really good. I got this from Mr. Shamberry, kind of had this as a lovely a lovely kind of sheet to, teach you as you go. So hopefully this one helped you as well. And I kind of just wanted to give you guys a lot of opportunities to, go through this and just get comfortable with dealing with velocity time graphs. So on a separate sheet of paper, you guys should have shown all your work for the accelerations of the object in all of these different spots. So to find acceleration, again, we're going to do that by finding the slope of this graph. So from 0 to 4 seconds, we're looking at this chunk of the graph here. So we need to find the slope of that graph. And the slope is going to be 0.75 meters per second squared. And it's going to be a positive value. So that's 0.75 meters per second in the positive direction. So here we don't have an actual direction associated with that, so we'll just say forwards, right? Our rate of acceleration from 0 to 4 seconds is 0.75 meters per second squared forwards. Then part B, what is the acceleration of the object from 4 to 6 seconds? So this time we are looking at this section of the graph. Hey guys, what's the slope of a flat line? If you said 0, you'd be right. So it's 0 meters per second squared is the acceleration from 4 to 6 seconds. All right, now let's look at the next section from 6 to 8 seconds. Oops. So from 6 to 8 seconds, we're looking at this section here, right? We've got to find our slope. So we go up here, we go up and over, right? So if we're finding slope, so we're going from 3 to 6, so this is 3 meters per second. It's a positive value. And then we go over 1 second. So the slope here is going to be 3, and it's a positive value. So the answer to our question is 3 meters per second squared, and it's positive again, so we're saying forward, right? And then our acceleration from 7 to 10 seconds, which is this last part here, we're gonna do the same thing. 7 to 10 seconds going down. Now we've got to find the slope here, so I'll find the slope, and we can do that kind of anywhere along the line, right? As long as we see the slope is constant, we can do it kind of anywhere. So now I'll do it from that point to that point. So we have 2 meters per second. And I do want to emphasize here, this is a negative value here. Negative 2 meters per second. Oops. Squared, or not squared, meters per second. So we're losing 2 meters per second every second, which means we have an acceleration of 2 meters per second squared, but we got a negative answer, so that means backwards. Now, one thing that I want to reiterate to you guys, these directions do not tell us the direction the object is moving. These are the directions of the acceleration. So this is the direction the object is being pushed. It's not necessarily moving that way. So that's the direction of the push that's causing a change in speed. So now let's get into describing motion, right? And as we've talked about describing motion, hey man, that's just velocity. We want to know what's happening to the velocity of the object. And as Mr. Shamberry said in the instructions, we want to hit the 3 things that we talked about. We want the amount of speed that an object has, right? We want the direction it's traveling and whether or not that speed is changing.
It's 3 o'clock.
Oh.
3 hours later.
All right, we're back. I don't know if you guys heard that, but it was 3 o'clock. I had to go pick up my kid from school. Forgot because I was making this video. So now we're back. We're back to it. And let's get right into describing the motion of these objects. So describe the motion in each of the segments. We're just going to go up to the graph here and go through each piece. So from 0 to 4 seconds, we're going to describe the motion of the object here in this highlighted area, right? And again, we need to talk about velocity. And velocity is right here on our y-axis, guys. So all we've got to do is look at the numbers and give our answer. So first, let's get the magnitude, right? Well, I'm going to see that that magnitude, that amount is changing. We start down here at 0 meters per second and we end up here at 3 meters per second. So I would say the object is increasing its velocity, moving forward, right? Because we have positive velocities the entire time, moving forward, and from 0 to 3 meters per second. So I got the amounts, whether or not that's changing, the velocity is changing, and the direction. So now let's look at the next section. So from here to here, what do you guys think is happening? Well, we're at a constant speed here. The velocity is 3 meters per second. It's positive, so we're moving forward, and it's not changing. So we have a constant speed. From here to here, okay? Our velocity is increasing. It's changing over time. From 3 meters per second to 6 meters per second. So there's the amounts. And we're moving forward, right? Because those velocities are positive. And last but not least, this section. Okay? What do you think the direction is for this section? What'd you put down? Well, guess what? It is not backwards, right? This is a velocity graph. So what's happening here is the velocity of the object is going from 6 meters per second down to 0 meters per second. It's changing, right? And it's moving forward the entire time because the velocities are all positive. So in this whole graph, at no point was the object moving backwards. So now let's go to some of the other questions that Mr. Shimberry put on this sheet. He has some really great questions down here. During which interval of time, if any, was the object not moving? Briefly explain how you know. So the only time the object was not moving would be any time it had a velocity of 0. So where does this line have a velocity of 0? There and there, right? So we would say at 0 seconds and at 10 seconds, right? I think it's tempting to say this flat section as well, because that would be correct for a position versus time graph. But we're looking at a velocity versus time graph. I think that's going to be the toughest thing, guys. As you go on to your Castle learning assignment here, it's going to jump back and forth between position and velocity graphs. So one of the tough things, and one of the things you guys are going to have to do, is be able to jump back and forth between them, making sure that you figure out which is which. All right, let's go back to some of these other concept questions we have. Which interval of time had the greatest magnitude of the acceleration? So remember, direction doesn't matter when we say magnitude, right? We just want the amount. So I'm going to look for the steepest slope here. And if I look, this section right here clearly has the steepest slope. So it would be from 6 to 7 seconds. We have that steep slope there. These are where they get interesting. During what interval of time was the object not accelerating? So this is where we have to look for a slope of 0. So remember, on a velocity versus time graph, hopefully you have the chart from the earlier problem set, to find the acceleration of an object, we look at the slope. So I'm going to look here and I see, oh, it's flat, which means we're at a constant speed, which means we are not accelerating. By definition, acceleration is a change in speed or a change in velocity, and at that flat part here from 4 to 6 seconds is the only spot where we're not accelerating. If this car was on a flat road, which intervals is the driver most likely pressing on the gas pedal? So when you press on the gas pedal of a car, what happens? Your velocity increases. So that would be like from here to here and from here to here. In both of those segments, we're increasing our velocity. And the next question is, where would we likely be pressing on the brake pedal if we were on a level road? And that would probably be here, because when you press on the brake, traditionally cars tend to slow down. It's getting a little weird with electric cars now. Is it even called a gas pedal? I don't even know. And then some of them slow down just when you take your foot off the gas. It's really weird. I don't know what the future holds for cars, man. It's kind of sad. All I know is no one can afford cars right now. Anyways, so some great questions, but now down to the tougher ones that we kind of already went over in the first part of this video, how to find displacements. So can we calculate how far the car has traveled in the first 4 seconds? So what we'll do is we'll draw a line along, use the, no, that's both not good. Let's draw a line along our graph here and another line along the x-axis for that same 4-second interval, and find the area of this shape that we create, which ends up being a triangle. So I'll just do my work over here. Area equals 1/2 base times height for a triangle. So I'll substitute my values in. 1/2, the base of the triangle is 4 seconds, and the height of the triangle is 3 meters per second. You love to see it. One of the cool parts, again, that I'll emphasize is those units cancel out. We end up with meters, so we're going to end up with a final answer here of 6 meters. Right? 4 times 3 is 12. Half of that is 6. So we get 6 meters traveled here just in that first section. So let's get rid of our work and get to the next question here, the next displacement. How far does the object travel from 4 to 6 seconds? So we'll go from 4 to 6 seconds here. So go along there and go along there, right? Looks like we're going to be making a rectangle. So in this rectangle, we're going to do base times height. So that's going to be 2 times 3, which is going to be another 6 meters. Then we get into the fun part. How far does this object travel from 7 to 10 seconds? So we're actually skipping a little portion. We're asked how far it travels from 7 seconds to 10 seconds. So we're going to be along this line here. And then I'll draw from 7 to 10 seconds on the x-axis, and I'll make whatever shape we got. It looks like we've got ourselves another nice triangle. So we'll do 1/2 base times height again. So why don't we take out the old calculator here and give it a go. So we're going to do 1/2 the base, which in this case is 3 seconds, times the height, which in this case is 6 meters per second. Throw that in and we get 9 meters there as our distance traveled. Now, I like Mr. Shimberry's question. Great questions, obviously. He's a great teacher. For all of these, he says, is this displacement forward or backward? Well, for all of these, when we plugged them in and did the work, were there any negative numbers involved? No. So mathematically, we could say, oh, we have no negative numbers, right? So that means we were always moving in the positive direction, which in the case of this problem is forward. So at no point were we moving backwards. The velocity of the car the entire time is positive. Therefore, we were always moving forward. Okay? So any way you want to look at it, all of those ways are ways of justifying your answer to this question. And I believe that wraps it up for this. So I'm hoping that going over all of these problems today with you guys really helped out. Hopefully this will allow you guys to feel a little better about the CASEL Learning Assessment that's due on Thursday. This will be your final grade for the quarter. Then please use the rest of the time in class this week to make up work here. I don't want to have anybody to have any missing work. I will accept any late homeworks, any late lab reports. Just give me something, guys, so I can get you some kind of late credit for all the work. I don't want you guys to, feel like you missed out on some points for any reason. So any late work, make it up. I know Portal's not up to date because turns out, having a small child at home and then also having a toddler that's home a lot of the time, didn't have as much free time as I thought I was gonna have. So haven't gotten those grades into Portal yet. So just double check on Google Classroom, everything from when I left to now. look at those numbers, make sure you've submitted to all of them, just read the descriptions. So take some class time to do that. I'm gonna give you guys that time. I don't think there's a lot of work assigned this week. Next week we'll jump in with some cool new stuff, which I think will be fun. We got a lot of videos to watch via a video. It's a video in a video, what? So we'll be doing that. Hopefully you guys can watch this and get set up for success for that final assessment grade at the end of the quarter, and we should be good to go. All right, Mr. Bell signing off, and I will see you guys in the next one.